Hey everyone, welcome. If you're a student just diving into the world of mechatronics, then this explainer is exactly for you. We're going to cut right through all the noise and give you a really solid, no-nonsense guide to the core concepts you absolutely have to know. So let's get right into it. So to get started, let's just think big picture for a second. Think about those huge industrial robots on an assembly line, the drones you see buzzing overhead, or maybe even the smart appliance in your kitchen. I mean, they seem totally different, don't they? But they all share a kind of secret ingredient. What do you think it is? The answer? They are all mechatronic systems. And look, this isn't some tiny niche field. This stuff is literally everywhere. We're talking about industrial automation, advanced robotics, incredible assistive technology that changes lives, safety and security systems, the entire future of transportation, and even how we monitor our environment. Mechatronics is kind of the invisible brain and nervous system behind so much of our modern tech. To make sense of all this, we're going to follow a pretty simple blueprint. First up, we'll look at the actual physical hardware, what I'm calling the toolkit. Then we'll dig into the data, which is really the system's language. After that, we'll explore the control logic that makes the whole thing smart. And finally, we'll talk about how you actually build this stuff and, more importantly, prove that it works reliably. Okay, let's kick things off with part one, the physical toolkit. Because look, before you can write a single line of code, you have got to understand the hardware that code is going to be running on. So a really critical idea to get right from the start is the difference between a microcontroller and a CPU. Just think of the CPU as the core brain. It's the part that does the actual thinking. But a microcontroller, well, that's the whole package. It's like a computer on a chip. It has the CPU inside, sure, but it also has memory and all the other bits and pieces it needs to interact with the real world. That's what makes them so perfect for embedded systems like a robot or a drone.
All right, so how does that CPU brain actually think? Well, it uses something called an instruction set. You can think of this as its entire vocabulary of actions. Every single operation it knows how to do, like loading data, adding two numbers together, or making a decision, it's all in there. It's the fundamental language that's baked right into the hardware itself.
And where does the CPU do its immediate moment-to-moment work? That happens in the registers. These are these tiny, lightning-fast storage spots right there on the chip. Some of them hold memory addresses, basically telling the CPU where to find information, while others hold the actual data it's crunching right at that second. It's kind of like the CPU's own personal scratchpad. So, you might be wondering, why do we care about all this low-level hardware stuff if we're just programming? Well, it matters a lot, because these physical limits directly shape your code. The size of the registers, for example, determines the biggest number you can work with in one go. The specific instructions available will change how you structure your program for efficiency. It's this crucial link between your software and the physical world of the chip. Okay, let's zoom out from the chip for a second and look at the rest of the system. You've basically got three key players. First, you have sensors. These are the system's senses, right? They detect things like light, temperature, motion. Then you have actuators. These are the muscles. They turn electrical signals into actual physical movement, like motors spinning. And finally, you have end effectors. These are the hands of the system, the grippers or tools that actually do something to the world. Senses, muscles, and hands. Simple as that. All right, let's move on to part two, the system's language. So we've got our hardware. Now we need to understand the information, the data that's flowing through it all. Now, the key insight here is that not all data is the same. In mechatronics, we're usually dealing with three really important types. You've got your operational data. That's the live stuff, the real-time readings that drive what the system is doing right now. Comparing the current motor speed to the speed you want it to be at. Then there's diagnostic data. This is for troubleshooting, for finding problems, logging things like motor voltage or error codes to figure out what went wrong. And finally, there's optimization data. This is what you collect over time to make the whole system better, like tracking how it responds so you can tune your algorithms. And hey, here's a professional habit you should get into right now. For every single piece of data your system uses, you need to define three things: its units, its expected range of values, and how often you're sampling it. Seriously, is it in degrees Celsius or Fahrenheit, millimeters or inches? Doing this from the start will save you from a world of confusion and really nasty bugs later on. Okay, on to part three, the guiding logic. This is where we give our system its intelligence. We've got the body, we've got the language, now we need the brain's control patterns. At the highest level, there are two fundamental patterns here: open loop and closed loop control. An open loop system is kind of like throwing a ball. You issue a command, and then you just hope for the best. There's no feedback. It's simple, and it's fast. But a closed loop system, that's more like trying to balance a stick on your hand. You're constantly using feedback.
in this case your eyes, to see the error and make corrections. It's definitely more complex, but it's also way more accurate and stable. So this right here, this is the very heart of closed-loop logic. It's just a constant cycle of correction. Step 1, you read the sensor to figure out where you are. Step 2, you calculate the error. That's just the difference between where you want to be, your set point, and where you actually are. Step 3, based on that error, you compute a new output command. Step 4, you send that new command to your actuator. And step 5, you do it all over again. You just repeat that loop, constantly trying to drive that error down to 0. And that brings us to our final section, part 4, build it, prove it. We've covered the theory. So how do we turn all this into a real, working, reliable device?
You know, you don't just jump straight into building the final thing. The smart path, the professional path, is to design your logic first, maybe on paper or in software. Then you simulate it to test its behavior and catch bugs early. Once that simulation looks good, then you build a simple prototype, maybe just on a breadboard, to make sure your core ideas actually work in the real world. Trust me, this process saves an incredible amount of time and frustration.
Now here is a concept that is absolutely critical for making things reliable: power budgeting. You have to figure out the maximum possible current all your components will ever draw at once, and then you add a safety margin, some headroom. And just as important, you have to separate your power circuits. Keep the noisy components, like motors, away from your sensitive logic circuits. If you don't, the electrical noise can make your microcontroller glitch and crash in ways that are almost impossible to debug.
So you've built your device, it's on the bench, and it seems to be working. But are you sure? How do you go from, hey, it worked that one time, to proving that this is a properly engineered, reliable system that will keep working?
Well, the answer is rigorous testing. I'm talking about multiple layers. You have unit tests, which check tiny individual functions in your code. You have subsystem tests, where you check a whole component, like the motor controller, in isolation. You need repeatability tests to make sure it does the same thing over and over. And finally, acceptance checks. These are your hard, measurable, pass-fail goals, like the arm must stop within 100 milliseconds. That's how you prove it really works.
Okay, let's bring this all home. We want to make sure you can walk away from this and confidently explain these concepts. So let's just run through a quick scenario. Imagine you're in a lab, or maybe it's an exam, and you're shown a block diagram of some kind of control system. The professor points to it and asks you to analyze it. What are the key things you should immediately look for and point out to show that you really get it?
Here's your 4-point checklist. First thing, right off the bat, state if it's open loop or closed loop. The dead giveaway is the feedback path. If you see one, point right to it. Next, identify the set point. That's the target, the desired value the system is trying to hit. And finally, name the manipulated output. That's the actual thing the system is controlling, like the voltage to a motor or the position of a valve. If you can nail those 4 points, you've just shown you understand the core logic instantly.
And that really brings us to the most important takeaway of this whole explainer. Look, anyone can tinker around and get something to work once, but the real challenge and the whole point of being an engineer is to build a system that you can test, you can verify, and you can prove is robust and reliable every single time. And that right there is the difference between a hobby project and real mechatronics engineering.